Okay, so this is for chapter 21 video assignment 2. It asks us to propose a nuclear decay chain by which radioactive molybdenum 109 decays to become silver 109, requiring several steps. So looking at the periodic table, we have, molybdenum there, which with 42 protons and an average molecular weight of 95.95, and then it asks us to create a mechanism by which it decays to silver 109. So because of what is given to us, we find that the number of nucleons does not change between molybdenum and silver 109. So we need to find a decay that will we need to find a decay that will decrease the number of neutrons and increase the number of protons, or just increase the number of protons, right? So we find that beta decay, where a neutron becomes a proton, giving off a beta particle, is the most likely to be able to help us explain this decay of molybdenum 109 to silver 109. So we have a little chart here. Beta decay, neutron becomes proton in this decay. So I have a type of graph. Number of protons increasing as we go to the right, and then the number of nucleons staying constant all the way throughout the mechanism. Now this first step I kind of wrote it out fully. The last steps I kind of shorthanded it. But here we have 42 protons in molybdenum and 109 nucleons, neutrons, and protons, decaying to, what is this, technetium, which has 43 protons. And because of that, we know that one of those neutrons turns into a proton. The neutron splits into a proton and an electron. Unholy offspring, I think, is how Dr. Horn described it. So that is that reaction that we have there. This is called a beta particle, right? So then we take TC109, and that decays to Ru44 with 44 protons, right? But still with 109, so that neutron becomes a proton again, giving off a beta particle. And then here we have RH109 with 45 protons, giving off a beta particle, decaying to beta particle plus PD109 with 46 protons, and finally we make it to silver 109. So as you can see, the number of nucleons does not change, which shows that the number of neutrons is decreasing while the number of protons is increasing. Now step 2, examining this proposed mechanism and seeing why some steps are very unlikely to occur. We see that in the periodic table. Oh boy, it's bad lighting. Silver is the only one that's even very close to that molecular weight of 109, right? It is very unlikely that we would find molybdenum in nature, right? Having a molecular weight that high, having only 42 protons with an average number of, 54 neutrons, but suddenly increasing that number of neutrons by like 12 more. Like it's very unlikely. So for us to even be able to get to that point, to be able to decay to there, it's very unlikely. And it's honestly the same with technetium. It has a molecular weight of 97. So finding something in nature of 109 to even decay is very unlikely. Same thing with ruthenium and even with rhodium. Palladium and silver are really the only likely ones that we'd find in nature of a molecular weight of 109. So that is one way that we could see how this mechanism really isn't likely, but that is how it technically could happen with beta decay.